Chapter 5: Power Projection Tactics in Cyberspace. Software cannot substitute for the physical constraints encountered naturally in other disciplines. Without a harsh and uncaring nature forcing us to make hard choices, we are willingly seduced. G. Frank McCormick. Section 5.1 Introduction. At this point, the reader may be wondering, what does all this talk of abstract power hierarchies, physical power, and warfare have to do with software? The answer is simple. It has everything to do with software, because in the 21st century, the world's largest abstract power hierarchies are encoded via software rather than rules of law. For example, Facebook, Google, Twitter, and Amazon, which have substantially more users than governments have citizens, are all software-encoded abstract power hierarchies. Every person or institution that has software-instantiated control authority over our computer networks and the programs running on them, from which we tacitly need their permission to send, receive, or store our digital information, is operating within an abstract power hierarchy, and we have established that abstract power hierarchies become dysfunctional and eventually lead to war. This chapter links together key concepts in computer theory and cybersecurity that are needed to understand why software is fundamentally a new type of abstract belief system, which gives a select few people abstract power and then entrusts them not to exploit it. People subscribe to these belief systems similar to how they subscribe to other belief systems, which make them systemically vulnerable to exploitation. People in control of our software wield a new form of abstract power. Much like the clerics and lawmakers of the past, modern software developers have adopted the habit of using encoded logic to give themselves special permissions and authorities which give them asymmetric control authority over a new type of essential resource that has emerged in 21st century society: bits of information. The way we have built our computer networks and designed our software systems has caused the people in charge of the most popular software we use to gain immense abstract power and control authority over our digital age resources. Consequently, everyone who uses this software is systemically vulnerable to exploitation and abuse. This would imply that a new form of God King is rising in the 21st century, except this time they're in control of our digital resources, rather than our traditional agrarian resources. Consequently, how we establish control authority over our data appears to be emerging as one of the most contentious intraspecies property disputes of the modern era. To believe that society will be able to constrain the far-reaching and asymmetric abstract power of these neo-God kings using more encoded logic, usually in the form of more regulations or more software, is to ignore 5,000 years of our predecessors' attempts to logically constrain the abstract power of previous rulers at the top of their respective abstract power hierarchies. Whether they're written using parchment or Python, society has already demonstrated beyond a shadow of a doubt that logical constraints are not sufficient to protect people against the exploitation and abuse of people wielding too much abstract power. If history and cultural evolution repeats itself, then sooner or later, people are going to have to start using large quantities of physical power to decentralize control authority over their digital information and secure their digital property rights by imposing severe physical costs on oppressors who try to exploit them through software. To believe that people won't eventually resort to physical power to secure themselves is to ignore the lessons of history. Using the core concepts of power projection theory established in the previous 2 chapters as a new frame of reference, we can observe the state of the world today and see the signs of digital age systemic exploitation and abuse of our digital infrastructure practically everywhere. Weaponized misinformation, troll farms, bot farms, Sybil attacks, denial of service, DOS, attacks, hacking epidemics, wide-scale online fraud, online censorship, shadow banning, routine data leaks, state-sponsored surveillance through entertainment apps, social network targeting campaigns, software companies routinely running ethically questionable social experiments on their users, unsupervised artificial intelligence controlling the primary information streams of billions of people, social media networks being captured by special interest groups, and amidst all of this, no reasonable expectation of privacy for any activity online. No matter where you go online, no matter what you do online, it has become standard practice for your valuable bits of information to be censored, surveilled, or sold to the highest bidder. Our bits of information are under the centralized control of the people who control our computer networks and the software running on those networks. Meanwhile, software companies are becoming asymmetrically wealthy and influential thanks to the data they're harvesting from the population. The evidence of population-scale systemic exploitation of people through their software is mounting. Except this time, the resource that technocratic god kings are competing for control over is digital information. Not surprisingly, in the age of information itself has become a precious resource. People's ability to assemble, collaborate, speak freely, and to exchange valuable resources like money is increasingly facilitated by software, which means these vital social functions are increasingly under the complete control of the people who control that software. This begs several important social questions. How could people secure themselves against the growing threat of digital oppression by a technocratic ruling class? Should our rights, particularly our property rights, our speech rights, and our rights to defend ourselves, not apply to our digital infrastructure and its corresponding digitized information? Is it possible to take back control of our digital information? How do we secure ourselves against systemic exploitation and abuse of our data streams by people who wield extraordinary amounts of abstract power over them because of the software and computer networks they control? Is it reasonable to believe that we should simply trust in our technocratic ruling class not to exploit our data streams for their own personal advantage? Is it reasonable to believe that we will be able to secure our digital information if we simply find a better combination of logic to constrain a software engineer's abstract power, despite having 5,000 years of written testimony to suggest that attempting to constrain people from abusing their abstract power using encoded logic doesn't actually work? 10,000 years of warfare would suggest that the most effective way to keep people's rights secure against attackers is to figure out a way to impose severe physical costs on those attackers. The solution to the emerging threat of systemic exploitation via software seems clear when viewed through the lens of power projection theory. To secure our digital information and infrastructure, we have to find new power projection tactics, techniques, and technologies which give people a way to impose severe physical costs on people wielding too much abstract power and control authority over our digital information. The solution makes rational sense, but it's not yet clear what the tactics, techniques, and technologies will be. Enter Bitcoin. With a background in power projection theory now thoroughly established, we can see Bitcoin in a new light. Bitcoin is compelling not as a candidate monetary system, but as an electro-cyber security system. Bitcoin's underlying proof-of-work technology is proving itself to be a successful way to physically secure bits of information against systemic exploitation and abuse by giving people the ability to project physical power to impose severe physical costs denominated in watts, on belligerent actors who try to exploit people through their software. Bitcoin demonstrates that people can gain and maintain zero-trust, permissionless, egalitarian, and decentralized control over bits of information, so long as they are willing and able to project physical power to secure it. This would suggest that Bitcoin isn't merely a monetary system, but perhaps some kind of soft form of power competition that has successfully replicated the same complex emergent benefits of warfare, less the destructive side effects. Through the ongoing global adoption of Bitcoin, people appear to be building the largest physical power-based dominance hierarchy ever created in human history, and the social implications of this could be extraordinarily destructive to all existing power hierarchies, including and especially nation-states. If the theories presented in this chapter are true, they would imply that Bitcoin represents far more than just a monetary system. After all, bits of information secured on the Bitcoin network could denote any type of information, not exclusively financial information. Instead, Bitcoin could represent a completely new system for securing any and all information in cyberspace, a way to keep bits of information secure against belligerent actors using physical constraints, not logical constraints. This could not only be revolutionary to the field of cybersecurity, but it could also be transformational to the field of physical security in general, to include national strategic security. To understand all of these concepts in further detail, it's necessary to rewind back to the early development of computers and to retrace the technological steps we took to get to where we are today, all while leveraging our newfound knowledge in power projection tactics in nature and human society. To that end, we begin the final chapter on power projection theory with a review of computer theory. Section 5.2 Thinking Machines. Innumerable activities still performed by human hands today will be performed by automatons. At this very moment, scientists working in the laboratories of American universities are attempting to create what has been described as a thinking machine. Nikola Tesla. Section 5.2.1 General Purpose State Mechanisms. 2 years following Tesla's death, a Hungarian-American mathematician, physicist, and engineer named John von Neumann summarized novel theories on electronic computing in a report prepared for the U.S. Army Ordnance Department. The report, titled Preliminary Discussion of the Logical Design of an Electronic Computing Instrument, explained technical ideas for the design of a fully electric general-purpose state machine, in other words, a computer, with a remarkable new capability, storing programming instructions as states within its own electronically accessible memory, so that it could do operations on its own programming, as if the machine had its own intelligence, experience, judgment, and mind. At the time this paper was published, programming state machines was a tedious ceremony involving days of lever pulling, dial turning, switch flipping, cable manipulation, and circuit plugging. Newman and his colleagues believed that electronically storable computer programs would represent a dramatic improvement to this process. To accomplish their idea, Newman and his colleagues reasoned they would need to build a machine that could store not only the digital information needed in a given computation, but also the instructions which govern the actual routine to be performed. One way to do this would be to find a way to convert manual instructions into numerical code. If orders to the machine are reduced to a numerical code, the report says, and if the machine can in some fashion distinguish a number from an order, the memory organ can be used to store both numbers and orders. It was in U.S. Department of Defense sponsored research like this paper where computer engineers began to communicate the enormous potential of what would eventually be known as software. The theoretical potential for general-purpose computing had been discussed a decade prior by mathematicians like Alan Turing, who predicted the feasibility of universal computing machines capable of implementing finite sequences of instructions to solve complex math problems. But it wasn't until the first general-purpose computing machines became operational that people like Newman began to practically demonstrate how they could be digitally instructed using their own memory. With 80 years of hindsight, we can read Newman's report and appreciate what might be the biggest understatements of the century when he made the claim that state machines capable of digitally converting human instructions into numerical codes would enable society to build machines that could conveniently handle problems several orders of magnitude more complex than they are handled by existing machines. After making this assertion, Newman and his colleagues went on to pioneer the development of the first stored program general-purpose state machine, also known as the modern computer. Computers are by no means new technology. Special-purpose state machines date as far back as 2,100 years ago to astrolabes like the Antikythera mechanism. In the 2 millennia following Greek astrolabes, the fundamental technological concept behind computers has not changed. They remain state machines, named after their primary function of computing things. People decided to name state machines after what they do, their function, rather than what they are, their form. This is perhaps because their function has remained constant while their form continually changes over time. A state machine's form can take many different sizes, shapes, materials, and complexities depending on what it's designed to compute. Nevertheless, the core function of computing discrete mathematical states has not changed over 2 millennia. So for all intents and purposes, state machines have remained the same computing technology. Prior to the early 1800s, state machines were special-purpose, non-programmable instruments used to assist people with very specific computations. The first viable general-purpose state machine and forerunner to the modern digital computer was the analytic engine designed by English mathematician Charles Babbage in 1833. Babbage's concept was novel because it meant people wouldn't have to build expensive, special-purpose instruments to make single computations anymore. One general-purpose state machine doubles as a nearly unlimited number of disembodied special-purpose state machines. Thus, by using a general-purpose mechanical instrument to perform multiple different computations, it would cause the marginal cost of computing to decrease, while simultaneously turning the act of designing a special-purpose state machine into a disembodied abstraction. This is a subtle but important distinction to make. Thanks to the invention of general-purpose computers, instead of having to build special-purpose state mechanisms to make computations, engineers only need to think of a sequence of operating instructions to assign to a general-purpose state mechanism. The act of computing changed from a manual, hands-on exercise to an exercise in abstract thinking. Unfortunately, the design of Babbage's analytic engine was too complex and expensive, and the benefits of general-purpose computing too poorly understood, for it to be manufactured in the 1800s, so Babbage never lived to see his mechanical general-purpose state machine built. Nevertheless, the mere concept of an operationally viable general-purpose state machine was revolutionary in the field of computing. Armed with a general-purpose state machine, a person could perform an extraordinarily wide range of specialized computations. For the first time, the primary limiting factor of computing was no longer the machine, but the imagination of its programmer. With the invention of general-purpose computing, the process of designing and building special-purpose state machines to perform specific computations became a disembodied, abstract concept, separable from the physical implementation of the machine making the computations. Machines which had previously been physically impossible or impractical to build suddenly became feasible, because instead of having to build a special-purpose state machine, a person simply needed to imagine what instructions they needed to give a general-purpose state machine. By following these instructions, the general-purpose state machine would, in effect, become the physical embodiment of a special-purpose state machine imagined by the programmer. This process of getting general-purpose state machines to role-play as special-purpose state machines is what's today known as ordinary computer programming. We take this for granted today, but in the early 1800s, this was a revolutionary engineering concept. Babbage's analytical engine was inspired by the design of Jacquard machines, devices fitted to looms that enabled complex textile patterns using punched cards to dictate the weave patterns of different colored threads. Borrowing from this design concept, the analytic engine was programmed using punched cards. The presence of a hole in the card indicated a symbolically important Boolean state like 1 or true, while the absence of a hole in the card indicated an opposing state like 0 or false. Using formal logical methods theorized by people like George Boole, who lived at the same time as Babbage, the sequence of holes punched into the card could issue a series of instructions to the state machine in a way that would mimic how a human might program a computer by pressing buttons, flipping switches, or turning dials. This technique for programming general-purpose computers was so effective that punched cards remained a popular programming technique for more than a century, until it was obsoleted by new technologies emerging in the 1980s. Although Babbage's analytic engine was too expensive to build, the disembodied and abstract nature of computer programming it enabled made it possible for mathematicians to write sets of instructions for Babbage's analytic engine, using nothing more than a published design concept. To that end, one of Babbage's students, a mathematician named Ada Lovelace, published the design concept of an algorithm in 1843 for the analytic engine to calculate Bernoulli numbers. By publishing these instructions, Ada Lovelace became the world's first computer programmer. This illustrates how the art of computer programming is an abstract and highly creative process, akin to writing a fictional story. Just like playwrights write stories for actors to perform, computer programmers write stories for general-purpose state machines to perform. Section 5.2.2 Stored Program Computers. Over the century following the publication of Lovelace's program, the emergence of new technologies like Boolean algebra and new technologies like electromagnetically controlled relays made programmable general-purpose state machines far more feasible to design and manufacture, reinvigorating interest in general-purpose computing during the 1930s. Having studied the 100-year-old design principles of Babbage's analytic engine, Alan Turing and other mathematicians started publishing theories about the feasibility of universal computation by machines capable of implementing finite sequences of instructions to solve complex problems. Inspired by Babbage, Harvard physicist Howard Aiken proposed the original concept for a general-purpose electromechanical computer, and began searching for a company to design and build it. International Business Machine (IBM) Corporation accepted Aiken's request in 1937, and after 7 years of design and manufacturing, delivered the first general-purpose electromechanical computer to Harvard in February 1944. Formerly called the Automatic Sequence Controlled Calculator, ASCC, but colloquially known as the Mark I by Harvard staff, this 9,500-pound, 51-foot-long machine was immediately commandeered for military purposes to assist with making computations for the U.S. Navy Bureau of Ships. Weeks after IBM delivered the ASCC to Harvard in February 1944, John von Neumann arrived on campus to commandeer the machine and put it to work on a series of computer calculations for a mysterious project he was working on. During this time frame, Neumann began to write highly classified computing algorithms for the machine, including some of the most common algorithms used today, for example, the merge sort. Impressed by the ASCC's general-purpose computing capabilities, Neumann quickly turned his attention to the work of John Mauchly and Presper Eckert, where he learned they had been commissioned by the U.S. Army Ballistic Research Laboratory to build something even more special than IBM's electromechanical machine, the world's first fully electronic general-purpose computer. The first fully electric general-purpose computer was commissioned by the U.S. Army Ballistic Research Laboratory and built for the U.S. Army Ordnance Corps to perform ballistic calculations for firing tables. Called the Electronic Numerical Integrator and Computer, ENIAC, Mauchly and Eckert's machine reduced artillery trajectory calculation time down from 20 hours to 30 seconds. One ENIAC replaced 2,400 humans. But immediately after it was built, John von Neumann once again appeared on campus, commandeered the machine, and put it to work on a series of different computer calculations for his mysterious project. This time, however, John von Neumann's mysterious project became far less secret. News of the Hiroshima and Nagasaki bombings stunned the world as the US president publicly disclosed the project on which Neumann and his colleagues had been working, the Manhattan Project. While the world celebrated the surrender of Japan, Neumann continued to, literally, plug away on the first fully electric, general-purpose programmable computer to help him design the next version of a nuclear bomb. Instead of punched cards, the ENIAC used plugboards as its state-changing mechanism. This allowed it to run a program at electronic speed, rather than the speed of a punched card reader. The trade-off to this approach was that it took weeks to figure out how to map a computing problem to the plugboard, and days to rewire the machine to execute each new program, in contrast to simply swapping punched cards. Nevertheless, ENIAC was a powerful calculating device that left an impression on Neumann and others who operated it. Its impressive capabilities, combined with how tedious and cumbersome it was to program, inspired Neumann and his colleagues to search for a solution on how to improve the machine by converting the state-changing mechanism from manual circuit plugs into electronically activated actuators. Then, by applying Boolean logic to the position of the actuators, this would allow programming actions to be digitized and stored as actuator states within the state mechanism. Stored program computers, Neumann theorized, would not only allow a computer to store its own programming instructions as states within its own memory organ, aka the state space dedicated to storing the information needed for computer programs. It would also allow the machine to automatically perform operations on its own programming instructions. Neumann believed this architecture would allow general-purpose state machines to handle problems several orders of magnitude higher than even the world's most powerful computers at the time, like the ENIAC he used to design the detonation device for the first atomic bomb. Inspired by the potential of these types of machines, Neumann and his colleagues wrote the aforementioned report to the U.S. Ordnance Corps. After getting funding and green light to design and build one, Neumann teamed up with Mauchly and Eckert to create the Electronic Discrete Variable Automatic Computer, EDVAC, the world's first stored program general-purpose computing machine. Section 5.3 A New, Exploitable Belief System. Lessons learned over centuries are lost when older technologies are replaced by newer ones. Nancy Leveson. Section 5.3.1 How to Talk to Thinking Machines. General-purpose and stored program computing were not only technological breakthroughs, they were also two major back-to-back leaps in human abstract thinking. The first leap in abstract thinking came when general-purpose state machines converted the exercise of computing from a physical machine-building process to an abstract design process. The second leap in abstract thinking came when computer scientists introduced methods for storing computer programming information as physical states on a state mechanism, using symbolically and syntactically complex protocols like machine code. Instead of applying symbolic meaning to specific audible waveforms or scribbled images like we do with the words we speak or the letters we write, early computer scientists figured out a way to apply symbolic meaning to physical state changes within a state machine. They accomplished this by applying mathematically discrete Boolean logic to state-changing mechanisms like switches or transistors to convert them into bits of information, in much the same way humans convert symbols or wave patterns into words. This gave rise to a new form of semantically and syntactically complex higher-order language, consisting of binary and multi-decibel symbols called machine code. From the broader context of metacognition and the evolution of human abstract thinking skills, it's hard to understate how remarkable machine code is. Stored program computing and the invention of machine code represent the emergence of an entirely new symbolic language, as well as a new medium through which syntactically and semantically complex information can be communicated. Using machine code, it is possible to convert practically any type of physical state-changing phenomenon in the universe into digitized bits of information. This is an important concept to remember for future discussions about Bitcoin, because the author will assert that Bitcoin represents the act of applying machine code to quantities of electric power drawn out of the global electricity grid. At first glance, machine code seems deceptively unremarkable. Sapiens have been creating and using higher-order languages for tens of thousands of years. We have been converting physical state-changing phenomenon like audible waveforms into information since we first discovered spoken language. So what's the big deal? What makes machine code so profound is the recipient of the information. Machine code was not invented for sapiens to communicate directly with other sapiens, but for sapiens to communicate directly with machines. Therein lies the significance of what computer engineers designed and built in the 1940s. They didn't just build gizmos, they invented a completely new machine-readable language, a medium through which humans can talk to inanimate objects using machine code, and just as astonishingly, a medium through which inanimate machines can talk back to humans. This new form of symbolic language created an entirely new form of storytelling, where people can communicate with each other indirectly and asynchronously through the computers they program, as shown in Figure 59, illustration of the difference between traditional language and machine code. By issuing computing instructions to a general-purpose state machine using a new form of machine-readable language, Newman and his team realized it would be possible for a computer programmer to produce practically any conceivable sequence of operational instructions because there is theoretically no limit to the state space. In other words, the number of different possible states that a general-purpose state machine can have. Since there is no theoretical limit to the size of the state space or the sequence of operations that a programmer can create using a stored program digital computer, each programmer has near unlimited design options and flexibility. With the right set of instructions, they can make a general-purpose computer perform any operation. Newman described this potential as follows. Quote, "It is easy to see by formal logical methods that there exist codes that are, in abstracto, adequate to control and cause the execution of any sequence of operations, which are individually available in the machine, and which, in their entirety, conceivable by the program planner." End quote. Newman explains how instead of having to physically execute a sequence of operations to instruct a general-purpose state machine how to behave, the programmer of a stored program general-purpose state machine simply needs to think about a sequence of operations in abstracto, that is, from a purely imaginary or theoretical point of view. Then, the programmer could use machine-readable languages to speak to the machine and tell it how to operate, rather than to manually operate it. These ideas were the precursor to what we now call operating systems. The important takeaway is that the computer operating systems are belief systems, not physical systems. Like all belief systems, modern computer programs are abstractions, figments of the imagination that are programmed into a computer rather than spoken or written. Therefore, like all belief systems, computer programs are vulnerable to systemic exploitation. With the invention of stored program computers and machine code, sapiens took a major leap forward in abstract thinking, and the socio-technical consequences of this major leap are not yet fully understood. Newman's stored program general-purpose computer removed many of the physical constraints of computer programming by moving the act of programming out of the domain of shared objective reality into the domain of shared abstract reality. Unbounded by physical constraints and with infinitely scalable state spaces, the primary limiting factors of general-purpose computer programming became the imagination and design skills of the programmer. Insofar as a computer programmer can think of a functional design and communicate it effectively to a general-purpose computer, a general-purpose computer can faithfully act it out. Section 5.3.2 A New Way of Storytelling. A core concept of computer theory is that computer programs don't physically exist. They are abstract concepts, hypostatized as concretely real things, for the sake of reducing the intellectual effort required to use stored program general-purpose state mechanisms. Although society has adopted the habit of describing software as if it were a physical thing that is loaded onto a computer, it simply isn't. And although society has adopted the habit of describing software as if it were comprised of an orientation of objects, for example, folder, trash can, recycle bin, thumbnail, it simply isn't. This is merely an abstraction technique used to make it easier to understand the complex emergent behavior of computer programs. Modern computers are usually made of complex circuitry and electrons stored in floating gate transistors. When a program is stored onto a computer, nothing is physically added to the machine. The computer remains the same general-purpose state machine built out of the same complex circuitry and electrons stored in floating gate transistors. When a program is removed from a computer, nothing is physically removed from the machine. Before a computer runs a program, all that physically exists is a state machine made of complex circuitry and electrons stored in floating gate transistors. While a computer runs a program and after it completes the program, all that physically exists is the same machine made of the same circuitry and electrons stored in floating gate transistors. At no point before, during, or after a computer program is added, removed, or executed does anything get physically added or removed from the system. The only physical change that occurs is a state change in the circuitry of the machine. A switch is flipped, or electrons move from one side of a floating gate transistor to another. A computer program is technically nothing more than symbolic meaning assigned to the state changes of a state machine. Just like sapiens learned how to assign symbolic meaning to audible wave patterns or visible shapes to form spoken and written language, they also learned how to assign symbolic meaning to state changes on a state machine using Boolean logic. In the case of machine code, the symbolic meaning assigned to a state change is usually binary code, like 1 or 0, which is enough to generate increasingly more semantically and syntactically complex information. This is one of the many reasons why computer science is such a fascinating, and difficult to grasp, field. Sapiens figured out how to apply symbolic meaning to computer circuitry, which can then repeat that symbolic meaning back to humans using communication protocols that humans can understand. Thanks to computer theory, we learned how to talk to machines and taught them how to talk back to us. Revisiting the core concepts of metacognition discussed in the previous chapter, the reader is reminded that within the domain of shared objective physical reality, the physical pattern of our spoken words, written words, and the states of our state machines have no inherent objective meaning. It takes a powerful human neocortex capable of abstract thinking to assign semantically or syntactically complex symbolic meaning to these phenomena. All computer programs are abstractions, figments of the imagination which do not physically exist as things with mass, volume, or energy in physically objective reality, completely incapable of producing their own physical signatures. Computer programs are imaginary concepts within shared abstract reality that are transferred from neocortex to neocortex using physical media, just like all forms of imaginary thoughts and ideas travel between sapient brains. A common source of confusion about computer science occurs when people conflate the physical media through which a computer program is communicated with the program itself. There is a major difference between an imaginary sequence of operating instructions spoken to a machine using symbolic language and the physical media through which those instructions are communicated to and from a computer. When programming a modern computer, what physically exists is the machine through which sapiens communicate their abstract ideas, using a carefully programmed sequence of state-changing operations. The rest is abstract. When a human speaks to another human, the audible waveform of their voice is physically real, but the symbolic meaning and information assigned to those audible waveform patterns is abstract. If a person were to believe that words are a physically real thing, they would be making a false correlation between abstract inputs detected by the brain, in other words, the symbolic meaning within a semantically and syntactically complex higher-order communication protocol, that were produced by their imagination, and their sensory inputs, in other words, the audible pattern detected by their ears. The same reasoning holds true for computer programs. Just because your eyes can see a computer acting out a program doesn't mean the program is physically real. You are looking at a general-purpose state machine, not a computer program. Like a painter's canvas, the digital computer is a portal through which an imaginary idea travels from one brain to the other. The person depicted in the painting isn't physically real. The only thing that is physically real is the paint and canvas through which the person's image is communicated to its viewer. Likewise, what the reader sees written on this page is not the author's ideas in and of themselves, but merely the medium through which the author's ideas pass from his neocortex to his reader's neocortex. Using the same logic, the switches on the circuit board and the electrons stored within floating gate transistors are not the program, but merely the physical medium through which an abstract idea is communicated from the computer programmer to the computer user. Section 5.3.3 Computers are electromechanical marionettes, acting out scripts written by neo-playwrights. To make the abstract nature of computer programming more digestible for readers who don't have computer science backgrounds, the reader is invited to reflect on Shakespeare's Romeo and Juliet. As previously discussed, sapiens use their abstract thinking skills to design virtual worlds within their minds, and then they get other people to envision the same world. In other words, synchronize their individual abstract realities into a single, shared abstract reality, via syntactically and semantically complex symbolic languages using storytelling. The story of Romeo and Juliet was an imaginary scenario conceived within the neocortex of a notable storyteller named William Shakespeare a little over 4 centuries ago. Our own neocortices can envision what Shakespeare imagined because Shakespeare used a symbolic language, English, as a medium through which he could share what otherwise existed exclusively within his imagination. The English symbols of Shakespeare's language were copied and printed onto pieces of paper and given to actors as instructions. These instructions are commonly called scripts. Actors speak and move according to the instructions received from their scripts. If Shakespeare did a good job writing these instructions, and if actors did a good job at following them, then a complex effect will emerge. An audience of people will be entranced by the performance, so emotionally captured by what they're watching that they'll forget that it's completely fictional. They'll forget that Romeo and Juliet don't exist anywhere except exclusively within their imaginations. Because of physical actions taken by role-playing actors in shared objective reality, people can see with their own eyes, aka sensory inputs, a physical representation of Shakespeare's imagination. Through the actor's performance, an audience can experience a full range of emotions that Shakespeare experienced when he first conceived of the story, even though many lifetimes have passed since the last synapse of his neocortex fired. Such is the beauty of storytelling and other forms of art, the ability to share one's ideas far beyond one's own physical limitations, long after one's tenure on Earth has ended. Nowhere in the sequence of events between Shakespeare's first imagination of Romeo and Juliet to an audience of people emotionally entranced by a theater's performance 400 years later did Romeo and Juliet become anything more than a fictional story. Based on the very definition of fiction, we know that Romeo and Juliet never physically existed. The fact that the story of Romeo and Juliet can be conceived by multiple different brains using tools like symbolic language printed on a physical script, physically spoken sound waves, or physically moving actors, doesn't mean that the story of Romeo and Juliet is anything except imaginary. Romeo and Juliet is merely an imaginary story told by a gifted storyteller. If someone were to argue that the imaginary story of Romeo and Juliet physically exists because it can be written, spoken, or acted out in physical objective reality, they would be guilty of hypostatization, the previously discussed fallacy of ambiguity. They would be doing that thing sapiens are instinctively inclined to do, where they believe something imaginary is something concretely real, because of a false positive correlation between matching abstract and sensory inputs, as illustrated in Figure 60. False positive correlation produced by the brain's realness verification algorithm. Because the motion of the actors matches a scenario imagined by the neocortex, people are quick to believe the imaginary scenario is physically real. Much like people who believe the king's abstract power is physically real, because knights display physical power when they get orders from the king, people will believe Romeo and Juliet is physically real because actors physically perform it based on the orders they receive from Shakespeare. Of course, it is a logical error to believe that a fictional story which exists only within the imagination is physically real just because the pages on which it's printed are physically real, or the stage on which it's performed is physically real and can be seen, smelled, touched, tasted, or heard. By now, the reader may be asking, what does Shakespeare have to do with computer programming? Simply change English symbols encoded on parchment to Boolean logic encoded on transistors, and replace the actors with electromechanical marionettes, and you get the modern art of computer programming. Computer programmers are, fundamentally speaking, storytellers. They conceive of fictional stories and create abstract descriptions of imaginary scenarios, events, objects, and ideas. Computer programmers write their stories using scripts, and they hand those scripts to machines, just like Shakespeare would hand his scripts to actors. Then, the general-purpose computers role-play according to the directions they receive in their scripts, just like actors role-play Romeo and Juliet. One could say that Romeo and Juliet is an imaginary story stored within the pages of a script, just like a computer program is an imaginary story stored within the circuitry of a computer. This is a technique computer programmers use to make it easier to talk about programming. For the sake of simplicity, engineers have adopted the habit of hypostatizing computer programs and treating them as if they were concretely real things comprised of concretely real objects. Like a form of shorthand notation, it's simply easier on the brain to communicate complex, abstract things like computer programs as if they were physically real things, because that's what we're used to experiencing. As the reader is no doubt experiencing right now, it's quite tedious to explain and to comprehend how computer programs actually work, so we simplify using abstractions. With the invention of stored program general-purpose state machines, sapiens created something more complex than they have the capacity to fully comprehend. Faced with the overwhelming complexity of modern digital computers, sapiens do what they have been doing since the Upper Paleolithic era. They put their neocortices to work, coming up with abstract explanations for things they can't fully understand. And they pretend like something imaginary is something physically real for the sake of simplicity. This is an extraordinarily helpful technique for reducing the metacognitive burden of managing the complexity of designing and operating computer programs. But it's important for the reader to understand that it's not technically accurate to describe a computer program as something physically real. This is an especially important point to understand prior to future discussions about Bitcoin. Computer programmers use syntactically and semantically complex symbolic languages like machine code, assembly language, or higher-order programming languages as a medium through which they share their ideas with machines, writing scripts for electromechanical marionettes to give a performance for an audience. These scripts and their corresponding symbols have taken many physical forms over the past 80 years. In the early days of general-purpose computing, these scripts were pieces of paper just like Shakespeare would have used, except with holes punched in them, rather than symbols written on them. But after the invention of stored program computing, scripts took the form of circuits built into digital computers. Today, scripts often take the form of electrons stored in floating gate transistors. General-purpose state machines can take different programmable states based on the instructions given to them by a computer programmer. If a computer programmer does a good job of imagining a fictional design and communicating it to the computer via symbolic language, and if the machine does a good job following its instructions, then a complex effect will emerge. A desired computation will be made, a desired behavior will emerge, and an audience will be so entranced by the performance of their electromechanical marionettes that they will become convinced what they see is something physically real. A well-programmed computer will cause a person to lose sight of the fact that they are sitting still doing nothing more than staring at an array of light-emitting diodes glued to a plane of glass and controlled by a general-purpose computer, all of which was painstakingly orchestrated across decades of engineering to present something which mimics the behavior of something observed in shared objective reality, but isn't actually there. It's as real as Romeo and Juliet. Nowhere in the sequence of events between a computer programmer's imaginary thoughts to an audience of people enthralled by an array of light-emitting diodes did the story written by the computer programmer become anything more than imaginary. Just like skilled playwrights and highly capable actors can write and follow scripts to make fictional tales like Romeo and Juliet look and feel physically real, so too can skilled computer programmers and highly capable machines write and follow scripts to make fictional tales like Solitaire look and feel physically real. People will become so moved by the performance of their general-purpose computers that they will completely lose sight of the fact that what they see is merely a canvas of symbols, an abstract representation of a completely virtual reality that would otherwise have no detectable physical signature if it weren't for the presence of the electromechanical marionette. The general-purpose computer is a machine commanded to live-action roleplay, LARP, according to whatever lies within the imagination of its programmer. Everything printed on the screen of a general-purpose computer is a computer-generated illusion. Whether it be a line of text, or a detailed image, or an imaginary object, or a three-dimensional interactive environment that looks and behaves just like environments experienced in shared objective reality, what a machine shows on a screen is virtual reality. Virtual reality is, by definition, not physically real. The only knowledge a person can gain from looking at a computer screen is symbolic knowledge, not experiential knowledge. This is true even if what's shown on screen is an image of something real or an event which did physically happen. A stored program general-purpose computer can therefore be thought of as a symbol-generating abstract reality machine. With the invention of digital computers, sapiens transformed their ability to communicate their abstract thoughts to each other to form a new type of shared abstract reality, which we have named cyberspace. Instead of applying symbolic meaning to spoken and written words, humans now apply symbolic meaning to electromechanical state changes in circuit boards. Instead of utilizing actors to role-play imaginary stories, they use machines. This is a core concept in computer science that is essential to understanding software's systemic security flaws. Section 5.4 Software Security Challenges. The first step in creating safer software-controlled systems is recognizing that software is an abstraction. Nancy Levison. This section gives a technological deep dive into some of the most challenging aspects of computer programming and cybersecurity. These concepts lay the groundwork for understanding how and why common cybersecurity challenges could be alleviated by physical cost function protocols like Bitcoin. Section 5.4.1 Software security is fundamentally a control structure design problem. If the total amount of money stolen from cybercrime were treated as its own country, then it would represent the third largest economy after the US and Chinese economies. In a special report issued by Cybercrime magazine, Cybersecurity Ventures stated that it expects, quote, global cybercrime to grow by 15% per year over the next 5 years, reaching $10.5 trillion USD annually by 2025, up from $3 trillion USD in 2015. This represents the greatest transfer in economic wealth in history, risks the incentive for innovation and investment, is exponentially larger than the damage inflicted from natural disasters in a year, and will be more profitable than the global trade of all major illegal drugs combined. End quote. Thanks in part to a substantial increase in nation-state-sponsored hacking activities, some have claimed that there is a hacking epidemic plaguing the modern field of cybersecurity, which will cause cyber attacks to increase at an estimated 10 times between 2020 and 2025. This may not be surprising to some people considering how routine ransomware attacks, data breaches, and other major cybersecurity incidents have become. Cybersecurity is now such a significant challenge for U.S. national security that the White House has recently passed an executive order addressing it. According to U.S. President Biden, improving the nation's cybersecurity is essential to national strategic security and stability. Quote, the prevention, detection, assessment, and remediation of cyber incidents is a top priority to this administration, President Biden has declared, and essential to national and economic security. Today's substantial amount of cybercrime suggests that software security engineering is challenging, and there is room for improvement. An important first step towards improving software security is understanding that software is fundamentally an abstract belief system, and all abstract belief systems are vulnerable to systemic exploitation and abuse. When software leads to unexpected or undesired behavior like a cybersecurity incident, People often claim their software broke, but this is just a figure of speech. Nothing physically breaks during a software malfunction, as it is physically impossible for something which doesn't physically exist to physically break. What actually happens during a software hack is that people find a way to exploit the software's design logic. This is why subject matter experts in software and system safety design like Levison assert that the first step to creating safer and more secure software-intensive systems is to remind yourself that software is only an abstraction. It's all in one's imagination. Computers behave exactly as they are instructed to behave. Therefore, when a computer produces an unexpected or undesired emergent behavior, the root cause of that behavior is most likely the design of the software. Except for very rare exceptions where computer hardware components are physically damaged or experience something like a short or an unintended bit flip, computers don't fail to operate exactly as they've been programmed to operate. By that same logic, unless the state-changing mechanism of a state machine has been physically impaired, there's also no such thing as a failed or broken state of a computer, because the machine was explicitly designed and built to be able to take that state. What usually happens when a computer program gets hacked or leads to a safety or security incident is that the original computer programmer attempts to encode logical constraints which are insufficient at stopping a belligerent actor from systemically exploiting the logic of the computer program. As many computer programmers have learned over the years, encoding logical constraints into software doesn't eliminate the threat of people exploiting the software's logic. It just changes the way the software's logic can be exploited. Note how this is the exact same concept discussed in the previous chapter about how laws don't prevent people from exploiting or breaking the law. Combining this observation with the fact that software can't break, then that means software security problems are fundamentally software design problems. If software gets hacked or behaves in a way that's unexpected and it leads to an undesired incident, it's almost always the case that the root cause of that incident was the result of the programmer producing a flawed design. Computers cannot be blamed for diligently and faithfully acting out the script given to them by their director. The script is to blame. This is a core concept in the field of software systems safety and security. Recall how a computer program represents a sequence of control signals issued to a state machine. All software-related safety and security incidents are the byproduct of control signals, which create insecure or hazardous system states, which then lead to an undesired loss event. The goal of software system security is to identify which control systems could lead to a hazardous state, and then design a control structure which eliminates or constrains those control signals. This is a foundational concept not just in software security engineering, but for system safety in general, as outlined by safety and security engineering techniques like STAMP and STPA. There are 4 primary ways software control signals can produce insecure or hazardous system states. First, software can provide a control signal that overtly places the system directly into an insecure or hazardous state. Second, software could not provide a control signal that is needed to prevent a system from being placed into an insecure or hazardous state. Third, software can provide a potentially secure control signal, but do it too late or too early, resulting in an insecure or hazardous system state. Lastly, software can stop providing a potentially secure control signal too soon or too late, resulting in an insecure or hazardous state. As discussed by pioneers in system safety and security engineering, the system's approach to improving security is to anticipate insecure or hazardous system states, using abstract thinking exercises like scenario planning, then to identify what control signals, or lack thereof, would cause the system to reach these undesired states. Once those sensitive control signals have been identified, the role of the security engineer is to design a control structure that either eliminates those control signals or constrains them as much as possible. To accomplish this, software security designers must keep strict account of all the different control signals, or lack thereof, a piece of software can execute. In system security theory, the root cause of all software security incidents is attributable to insufficient control structure designs, which didn't properly eliminate or constrain unsafe or sensitive control signals. Therein lies the fundamental challenge of software security engineering. It requires an engineer who can understand and anticipate different combinations of control actions or inaction which should or shouldn't occur. Software security engineers must be able to recognize these sensitive control signals and design control structures which eliminate or constrain those signals, which is quite hard to do using only logical constraints encoded into software, while still meeting desired functionality and behavior. This is one of the biggest challenges in software security, which makes it so different from security engineering in other industries. Because software doesn't physically exist, it's not possible to secure software using physical constraints unless the underlying state mechanism, in other words, the computer, is physically constrained. This is the single most important concept that the reader should note prior to a discussion about proof-of-work physical cost function protocols like Bitcoin, because what proof-of-work represents is the act of physically securing software by physically constraining the underlying computer. Why exactly is it so challenging to design software control structures which can eliminate or sufficiently constrain a computer from sending unsafe control signals using logical constraints rather than physical constraints? The author offers 6 explanations. First, computers can have infinitely expanding state spaces comprised of an infinite number of hazardous states. Second, programmed computers have shape-shifting protean behavior, which gives them unpredictable, non-continuous, thus non-intuitive, emergent behavior. Third, because it's imaginary, it's very easy to build software with unmanageable complexity. Fourth, software control signal interfaces are invisible and physically unconstrainable. Fifth, software design specifications are arbitrary and semantically ambiguous, and the software engineering culture of information hiding can also hide critical security information. Lastly, untrustworthy software administrators deliberately design systems which give themselves abstract power and control authority. Section 5.4.2 Software Security Challenge Number 1 Infinitely Expandable State Spaces with Infinite Hazardous States. The first reason why software security engineering is challenging is because the state space of most computers is practically infinite. As von Neumann famously observed, there is theoretically no limit to the number of states that a stored program general-purpose state mechanism can have. Unfortunately, this means there's also no theoretical limit to how many insecure or hazardous states a programmed computer can have. Consequently, as software becomes larger and more complex, the size of its hazardous state space increases exponentially, often far exceeding what computer programmers can reasonably expect to circumnavigate. This presents an extraordinary challenge for software security engineers who are responsible for understanding a given computer program's hazardous state space and designing control structures which eliminate or constrain control actions which would cause the system to enter that hazardous state space. If the hazardous state space is practically infinite, then it's practically impossible to avoid all hazardous states. Section 5.4.3 Software Security Challenge Number 2 State-changing mechanisms behave like shape-shifting monsters. The discrete nature of states also means a computer can have dramatically different emergent behavior despite minor state changes. A state-shifting mechanism can be thought of as a bipolar, shape-shifting monster. With a seemingly minute and inconsequential state change, a computer's emergent behavior can transform from something harmless to something significantly hazardous. This non-continuous behavior means computers are unpredictable and always one wrong move away from catastrophic malfunction. One seemingly minor control action, or inaction, can cause a discrete state change that causes a programmed computer to behave in surprising ways, and it is practically impossible for software designers to anticipate all the possible different combinations of unsafe control actions which could lead to every possible hazardous state change within a given state space. This means it's practically impossible for software engineers to know every single wrong move or unsafe control action a complex piece of software can make. Section 5.4.4 Software Security Challenge Number 3 It's very easy to make software unmanageably complex. Because software is abstract, and because state mechanisms have infinitely expanding state spaces, there is practically nothing limiting the complexity of the design of computer programs. In her book on systems safety engineering, Nancy Levison offers an explanation for why this can make software engineering exceptionally difficult, citing observations of subject matter experts like Parnas and Shore, and software's so-called curse of flexibility. Quote, "In principle," Levison explains, "software flexibility is good. Major changes can be made quickly and at seemingly low cost. In reality, the apparent low cost is deceptive. The ease of change encourages major and frequent changes, which often increases complexity and rapidly introduces errors." End quote. Shore explains software's curse of flexibility by comparing software engineering with aircraft engineering. When designing an aircraft, quote, Feasible designs are governed by mechanical imitations of the design materials and by the laws of aerodynamics. In this way, nature imposes discipline on the design process, which helps to control complexity. In contrast, software has no corresponding physical limitations or natural laws, which makes it too easy to build enormously complex designs. The structure of the typical software system can make a Rube Goldberg design look elegant in comparison. In reality, software is just as brittle as hardware, but the fact that software is logically brittle rather than physically brittle makes it more difficult to see how easily it can be broken and how little flexibility actually exists. End quote. Leveson argues that software makes dramatic and severely inappropriate design changes so easy to execute that it gives software engineers false confidence and encourages them to begin premature construction of a system, leading to poor designs that remain unchanged later in development. Few engineers would start building an airplane before the designers had finished the detailed plans, she asserts, yet this is the norm in software development. Another issue emerging from software's flexibility is the ease with which it's possible to achieve partial success at the expense of creating unmanageable design complexity. Quote, "The untrained can achieve results that appear successful but are really only partially successful," Leveson explains. Software works correctly most of the time, but not all the time. Attempting to get a poorly designed but partially successful program to work all of the time is usually futile. Once a program's complexity has become unmanageable, each change is as likely to hurt as to help. Each new feature may interfere with several old features, and each attempt to fix an error may create several more. Thus, although it is extremely difficult to build a large computer program that works correctly under all required conditions, it is easy to build one that works 90% of the time. End quote. Comparing this concept to the design of physical systems, Shore notes how inappropriate it would be to build an airplane that flies 90% of the time. Shore also notes how, for some reason, the general public often has few objections about software engineers attempting to build complex software without appropriate design knowledge and experience in the field they're writing software for. Few people would dare to fly an airplane designed and built by people who have no formal training or education in aerospace engineering. Yet people often have no problem entrusting software, to include safety or security critical software, to teenagers with no background in computer science or even the field they're working. Thanks to advances in computer programming languages, it is not difficult for people with no background in computer science, systems engineering, or systems security to teach themselves how to code. All it takes to learn how to program a computer is simply to take the time to understand a computer programming language, as if it were any other type of foreign language. And because computer programmers are often in high demand, it is also not uncommon for programmers to be hired to immediately start designing and building software infrastructures for major systems, with which they have no experience. Shore also notes how there is little physical or self-enforced discipline in software engineering, like there are in other fields of engineering, a trend which seems to continue despite how increasingly more reliant the population becomes on computer programs. He argues that the lack of physical constraints in software design and development creates extra responsibility on computer programmers to have the self-discipline not to produce overly complex and unmanageable designs which can lead to unexpected or undesired behavior. But many computer programmers shrug off this responsibility. Quote, like airplane complexity, software complexity can be controlled by an appropriate design discipline. But to reap this benefit, people will have to impose that discipline. Nature won't do it. As the name implies, computer software exploits a soft medium with intrinsic flexibility that is both its strength and its weakness. Offering so much freedom and so few constraints, computer software has all the advantages of free verse over sonnets, and all the disadvantages. End quote. Here, the reader should note how Shore makes a direct comparison between software and free verse written by storytellers. This is yet another reminder that the act of programming is fundamentally an act of writing a fictional story, a script for a computer to roleplay. Just like storytellers can produce abstract imaginary realities where they are completely uninhibited by the physical constraints of shared objective reality, so too can software engineers. Shore explicitly describes this as a disadvantage because it removes the natural forces which constrain complexity, prevent poor design, or stop a developer from producing designs which seem functional but are logically flawed and or physically impossible to engineer. This concept is illustrated in Figure 61, example of a logically flawed engineering design that's physically impossible. The flexibility of software, Levison explains, encourages us to build much more complex systems than we have the ability to engineer. This necessitates a type of self-discipline which she asserts may be the most difficult kind of discipline to find in the field of software engineering, deliberately limiting the functionality of software. Quote, theoretically, a large number of tasks can be accomplished with software, and distinguishing between what can be done and what should be done is very difficult. When we are limited to physical materials, the difficulty or even impossibility of building anything we might think about building limits what we attempt. End quote. In software engineering, this isn't the case. Just as easily as artists can come up with logically impossible designs, such as the bridge shown above, software engineers can easily create design concepts that are physically or logically impossible. Levison summarizes the danger of software design flexibility with a quote from systems engineer G. Frank McCormick. Quote, and they looked upon software and saw that it was good, but they just had to add this one other feature. Software temptations are virtually irresistible. The apparent ease of creating arbitrary behavior makes us arrogant. We become sorcerers' apprentices, foolishly believing that we can control any amount of complexity. Our systems will dance for us in ever more complicated ways. We don't know when to stop. A project specification rapidly becomes a wish list. Additions to this list encounter little or no resistance. We can always justify just one more feature, one more mode, one more gee-whiz capability. And don't worry, it'll be easy. After all, it's just software. We can do anything. In one stroke, we are free of nature's constraints. This freedom is software's main attraction, but unbounded freedom lies at the heart of all software difficulty. We would be better off if we learned how and when to say no." End quote. Section 5.4.5 Software Security Challenge Number 4. Software interfaces are cheap to produce and often invisible. Another reason why software engineering is exceptionally difficult is because software control interfaces are cheap to produce and invisible, making them easy to obfuscate. A common way to deal with the complexity of modern computer programming is to use systems engineering abstraction techniques like decomposition to break software down into separate modules. Although separating a program into different modules may reduce the complexity of individual software components, it doesn't reduce the complexity of the software system as a whole, and it can introduce unmanageable complexity into the design by creating a high number of invisible interfaces, which can become impossible to manage. In his journal article about the Software Aspects of Strategic Defense Systems, David Parnas describes how invisible and complex control interfaces represent a major challenge with software engineering, particularly when designing safety or security-critical systems. Quote, "The greater the number of small components, the more complex the interface becomes. Errors occur because the human mind is unable to fully comprehend the many conditions that can arise through the interaction of these components." End quote. Shore once again calls out how the lack of physical constraints in software can be a disadvantage. He makes the case that software interface design is more challenging than designing interfaces for physical systems. Quote, "Physical machines such as cars and airplanes are built by dividing the design problem into parts and building a separate unit for each part. The spatial separation of the resulting parts has several advantages. It limits their interactions, it makes their interactions relatively easy to trace, and it makes new interactions difficult to introduce. The interfaces in hardware systems, from airplanes to computer circuits, tend to be simpler than those in software systems, because physical constraints discourage complicated interfaces. The costs are immediate and obvious." End quote. Quote, "In contrast," Levison explains, "software has no physical connections, and logical connections are cheap and easy to introduce. Without physical constraints, complex interfaces are as easy to construct as simple ones, perhaps easier. Moreover, the interfaces between software components are often invisible or not obvious. It is easy to make anything depend on anything else." End quote. Section 5.4.6 Software Security Challenge Number 5. Software design specifications are arbitrary, ambiguous, and hide security-critical information. Do not try and bend the spoon. That's impossible. Instead, only try to realize the truth. There is no spoon. Boy Monk, The Matrix. The fourth reason why software security is so challenging deserves a more thorough explanation, as it relates directly to the justification for making this thesis. The bottom line up front is that computer engineers have adopted the habit of using arbitrary and semantically ambiguous terms to specify the functionality and desired, but perhaps not actual, emergent behavior of their software. This not only causes confusion about how software works, but it also suppresses vital information needed for security design purposes. Additionally, The arbitrary and semantically ambiguous way that software engineers describe their software creates a window of opportunity for nefarious software engineers to deliberately build exploitable design features and intentionally obfuscate them. Recall how computer program design represents an exercise in abstract thinking. Because software is imaginary, computer programmers must come up with imaginary explanations and abstract concepts to explain the emergent behavior of the computers they program. Then, people hypothesize these abstract concepts. They start acting like software abstractions are concretely real things. They forget that just because multiple people serendipitously decided to use the same abstract terms to describe the desired functionality and behavior of a given computer program doesn't mean these descriptions are objectively true, or that it's the only way to describe the function and behavior of a computer program. For whatever reason, probably because it's not necessary to understand computer science to write software, people keep falling into the same trap of forgetting the undisputed truth that all computer programs are abstractions, and can therefore be described any different way using any imaginary concept, abstraction, or metaphor. People don't know a basic lesson of computer science, that the way any software engineer chooses to describe the function, design, and behavior of software, including but especially its creator, is imaginary, arbitrary, and semantically ambiguous. This not only leads to pointless debates. People like to argue about what the right metaphor is to describe software, as if there's an objective answer, oblivious to the fact that there can't be an objectively right way to describe an imaginary abstraction. But it also leads directly to security incidents, because the metaphors we use often hide safety and security-critical design information. One of the more detailed and comprehensive explanations of the abstract and arbitrary nature of software design specifications comes from Charles Kruger, who first outlined the challenges of software design reuse in his research for the U.S. Air Force in the early 1990s. As Kruger explains, computer scientists and systems engineers use abstraction techniques to manage the enormous complexity of software. Abstraction is a popular technique in both systems and software engineering because it allows software engineers to suppress the details of a computer program that are unimportant to them, while emphasizing the information that is important to them. Modern computer programmers use multiple layers of nested abstractions developed over many decades. There's usually a minimum of at least 4 layers of abstractions nested within each other when modern software engineers write computer programs today. For example, the abstraction called machine code is further abstracted and nested inside the operations of an assembly language, which is even further abstracted and nested inside the operations of a general-purpose language, which is then further abstracted using software specification techniques like object-oriented design. When software engineers use semantic expressions like string, car, var, thumbnail, coin, token, application, or website to describe the computer programs they design, they are referring to nested abstractions that have been developed and popularized by computer programmers over decades. To the untrained eye, this abstraction technique can be confusing. Nevertheless, multi-layer and nested abstractions have proven to be quite helpful for software engineers, because they reduce what's known as cognitive distance. Kruger defines cognitive distance as the intellectual effort that must be expended by software engineers when developing a computer program. Abstractions reduce cognitive distance by allowing software engineers to filter out complex details about a computer program and focus on what's important to them. Quote, "Without abstractions," Kruger explains, "software developers would be forced to sift through a collection of artifacts trying to figure out what each artifact did." End quote. Quote, "The effectiveness of abstractions," Kruger explains, "can be evaluated in terms of the intellectual effort required to use them. Better abstractions mean that less effort is required from the user." End quote. The more an abstraction technique reduces the cognitive burden of thinking about software, the more popular it becomes as a mechanism not just to explain the intended function and complex emergent behavior of a computer program, but to inform the design of future computer programs. In a technique commonly known as information hiding, software engineers consider it to be a virtue to create abstractions which suppress as much of the technical details about a computer program as possible. The more information and details that are suppressed by a computer abstraction, the better it is perceived to be. At this point, it should be clear to the reader that if the goal is to hide as much information as possible, then it's going to lead to a breeding ground of confusion about how software is designed and how it actually functions. Kruger explains that the way software engineers decide to suppress or emphasize information using abstraction techniques, quote, "is not an innate property of the abstraction, but rather an arbitrary decision made by the creator of the abstraction. The creator decides what information will be useful to users of the abstraction and puts it in the abstraction specification. The creator also decides which properties of the abstraction the user might want to vary and places them in a variable part of the abstraction specification." End quote. In other words, the criteria that software engineers use to distinguish between important and unimportant artifacts of a design are arbitrary, and so are the metaphors they use to describe its desired function and emergent behavior. This point needs to be emphasized. Those who create and specify the design of software do so using arbitrary decisions about what to name it and what information they think is important to share about its design. There is no such thing as a technically precise software specification because software itself is an imaginary, abstract concept. One of the most fundamental concepts of computer theory is that the way any software engineer chooses to describe the function, design, and behavior of software is imaginary, arbitrary, and semantically ambiguous. Nobody, including but especially the creators of software who may have the most familiarity with its design, can claim to have produced a technically accurate or objectively true description of software, because all software descriptions are strictly abstract and imaginary concepts. Just because someone has technical knowledge about the syntax behind a piece of logic doesn't mean they're objectively right about its specification. Kruger goes on to break down the technical structure of software abstractions. He explains how all software engineering abstractions include a specification that explains what the software does. These specifications have syntactic and semantic parts. The syntactic parts of a computer program's specification manifest as the program's source code and the mathematically discrete operations implemented by that code. The semantic parts of the design specification are expressed using common language, independent from whatever computer programming language is used. In other words, software engineers describe the intended function and behavior of their programs in two different ways: through the source code itself and through the words and language they use to describe what the source code is supposed to do. The way computer engineers create abstractions to specify the design, intended functionality, and desired emergent behavior of their software therefore qualifies as an abstract language in and of itself, filled with its own semantically and syntactically complex structure. Recalling the concepts presented in the previous chapter, all higher-order languages invented by sapiens are both syntactically and semantically complex. Well, so too are the abstract specifications software engineers use to explain the intended function and behavior of their computer programs. Like with any language, there are opportunities for misinterpretation and miscommunication. Many of the semantic expressions used by software engineers are not uniform across the industry. Different terms can mean the same thing, or the same term can mean dramatically different things. This challenge is further exacerbated by the fact that most abstractions are popularized for their simplicity, not for their technical precision or accuracy. As Kruger explains, semantic specifications are rarely derived from first principles. Software engineers invent semantic expressions to specify the design and function of their software based on personal whims, using whatever abstract metaphors they want for any reason they want, in completely arbitrary and subjective ways. As an example, consider the computer programs which manage off-premises data storage called the cloud. This is an abstract and semantic description of data storage technology which is not based on first principles and not intended to be technically accurate. Cloud is a popular term because it offers a simple way to describe a technology. It reduces the metacognitive burden of having to stop and think about enormously complex data storage technology. Why is it important for the reader to understand how arbitrary and semantically ambiguous software abstractions are? Because software engineers notoriously forget this basic concept of computer theory. A common problem in the field of software engineering is that engineers keep overlooking the fact that the abstractions used to describe the intended function and behavior of software are intended to reduce cognitive distance. They're not intended to provide a technically accurate description of the design. Abstract software design specifications become popular because of how much information they suppress and how easy they are to understand, not how technically valid they are. Software engineers have an unfortunate tendency to forget this lesson of computer science, causing them to become overly reliant on popular, but technically inaccurate, abstractions to influence their design decisions. This can be extremely counterproductive to the goals of software security designers if the popular specification obfuscates security-critical control structure information. The fundamental problem is misaligned goals between software and security engineers. The goal of most abstractions and design specifications created by software engineers is to reduce cognitive distance, to minimize the amount of thinking required to understand the intended function and behavior of software, so that software design concepts can be understood as quickly as possible and reused as easily as possible. But as described previously, the goal of system security engineers is to understand what control signals a piece of software can send to a computer that could place it into a hazardous state, so that control structures can be designed which eliminate or constrain unsafe control signals. The software engineer's goal of suppressing as much information about a computer program as possible therefore directly conflicts with the security engineer's goals. The information being suppressed by an abstraction can include information that is vital to security design. Therein lies the problem with software engineers who forget how arbitrary, subjective, and semantically ambiguous their software design specifications are. It can cause them to inadvertently overlook vital security information, or in many cases, intentionally disguise vital security information, hence popular types of backdoor or trapdoor exploits. A lack of awareness about this issue at scale leads to poor security culture, where software engineers keep producing, promoting, or reusing abstract, non-technically accurate software design specifications that hide vital security information. The reason why this is so important to understand is because the author believes this is one of the major contributing factors to why Bitcoin is so misunderstood by the public. People seem to be missing vital information about Bitcoin's security or jumping to inappropriate conclusions about it because of an arbitrary decision by its inventor to describe it as a peer-to-peer cash system. People are constantly arguing about design specifications and constantly using completely arbitrary and meaningless categorizations like cryptocurrency or blockchain to describe Bitcoin, completely oblivious to the basic tenets of computer theory, which tell us that these are all arbitrary terms, founded on nothing more than personal whim. It is no more technically accurate to call Bitcoin a coin as it is to call data storage software a cloud. There is no need to learn graduate-level concepts in computer theory and system security to code software. This creates a problematic situation where people can devote their careers to writing computer programs without actually knowing the core tenets of computer science. Because they don't have backgrounds in computer science, they often don't understand how completely arbitrary, subjective, and technically inaccurate their software design specifications are. This makes them predisposed to using abstractions which suppress vital control signal information needed for security. It also creates a situation where a lot of software engineers have false confidence about how much they understand computers. It should come as no surprise then that this might lead to such pronounced problems with cybersecurity that a U.S. president has to pass an executive order to address it. Security-critical control signal information hidden by software abstractions is a major contributor of 0 days and other software security exploits. To hack a computer program is to take advantage of sensitive control actions. When a hacker hacks software, they simply execute, or withhold, control signals that were not properly eliminated or constrained by the software's design logic. Why were these sensitive control signals not properly constrained? In many cases, it's because software engineers overlooked them. Why did software engineers overlook these sensitive control signals? likely because they were using abstractions which suppressed vital information needed to detect the security design flaw. Hackers and nefarious software engineers thrive on making arbitrary, abstract, and semantically ambiguous software descriptions to obfuscate their exploitable design features. The adopted culture of abstraction and information hiding is where these belligerent actors derive their advantage. They will intentionally encode exploitable design logic into software and give themselves backdoor or trapdoor access to sensitive control signals. They deliberately design their software to enable unsafe control actions, which can place their target's computer into an insecure or hazardous state, which they can then exploit. To hide their nefarious design or subversive tactics, they create abstractions which deliberately suppress or distract people from critical information about their program's control structure. To illustrate the security challenges associated with arbitrary and semantically ambiguous software specifications, let's return to the example of the cloud. When some people save their sensitive data to the cloud, they think it works the same way as when they store it locally on their own computer. They don't realize they're sending their sensitive data to another person's computer. For obvious reasons, sending sensitive data to an anonymous person's computer represents a security hazard. But people often don't recognize the vulnerability because the public has arbitrarily adopted the habit of calling it a cloud, rather than external computers under the control of people we must trust not to exploit that control. It's easy for nefarious actors to come up with similar abstract software specifications using equally as arbitrary and semantically ambiguous terms designed to distract people from seeing security vulnerabilities, which would otherwise be obvious. To make matters even more counterproductive for security designers, software engineers often form inappropriate, rigid consensus about their abstractions. They will assert that one abstraction is correct, even though it is arbitrary and probably not derived from first principles. The reader is invited to test this out on their own by trying to convince software engineers to use a different name than cloud to describe data storage software. Security challenges associated with the arbitrary and semantically ambiguous nature of abstract software design specifications are further exaggerated by an uneducated public. As people increasingly incorporate software into their everyday lives, they gain a false sense of confidence and understanding about that software. They think they understand software's complexities because of how often they use it, or because they know what jargon to use in what context, despite how unfamiliar they are with computer theory or systems theory. This false confidence leads to further miscommunication and confusion about the merits of different software designs. It is not uncommon to see people with no background in computer science quibbling about the merit of different software designs. In the debate, people overlook how arbitrary and semantically ambiguous their jargon is in the first place. A good illustration of this phenomenon is object-oriented software design abstractions. The desire to minimize cognitive distance explains why abstraction techniques like object-oriented design became so popular in the 1990s. People live in a three-dimensional world, surrounded by an orientation of different objects. So it makes sense that people would find it easier to explain the complex emergent behavior of computer programs as if they were orientations of objects, despite how technically inaccurate this description is. Likewise, it's easier to design computer programs as if they were objects, and it's easier to communicate that design to other developers. For these reasons, object-oriented design has become one of the most popular software abstraction techniques. The decision to describe the intended function and behavior of a computer program as an orientation of objects is strictly an arbitrary decision based on personal whim. Computer programs are abstract beliefs that can be described as anything. From a technical perspective, it is just as valid to describe the complex emergent behavior of software as an orientation of objects as it is to describe it as a verb, function, or sequence of actions. People who don't understand computer science don't understand this basic principle of computer science. Consequently, they often, tacitly, assert that the only way to accurately describe the function and behavior of a computer program is as an orientation of objects. They will sincerely believe that cloud and token and coin and countless other terms are the only appropriate ways to specify the functionality of a given piece of software. Even more surprisingly, they will sometimes legitimately believe that abstract software objects like token or coin are real things, for no other reason than the fact that people adopt a universal habit of talking about them as if they were physically real objects. Nevertheless, while it may be popular to talk about software as if it were comprised of objects oriented in three-dimensional space, software is clearly not comprised of physical objects in three-dimensional space. As The Matrix famously reminds us, there is no spoon. All software objects are arbitrary abstractions which don't exist anywhere except within people's imaginations. The only things which physically exist are stored program general-purpose state machines, programmed to exhibit complex emergent behaviors that resemble what people arbitrarily choose to describe as a token, coin, or spoon. Just because computers can be programmed to present the image or behavior of a spoon doesn't mean that spoon is a technically accurate description of the software, nor does it mean the spoon is physically real. One would think this is obvious, but increasingly, it's not. People seem to have become so accustomed to talking about software as if it were comprised of objects that they have become to hypostatize abstract software objects as concretely real objects. It frequently appears as though the public has genuinely lost sight of the fact that software objects aren't real. Like Neo or anyone else who has spent too much time in cyberspace, the public seems increasingly less capable of remembering there is no spoon, that software is nothing more than a method of communicating abstract ideas. Like the gentleman pictured in Figure 62, modern agrarian Homo sapien losing his grip on physical reality. This can cause some people to lose their grip on reality and struggle to understand what's real versus what's virtual, because they have lost sight of the fact that all computer programs are nothing but programmed computers acting out purely fictional stories. This trend could have major implications on population scale security. The inability to make a distinction between abstract reality and physical reality could cause people to place themselves into situations where they can be exploited at massive scale through their software. In the modern era, the belief system through which populations can be exploited is not their ideologies, morals, ethics, or theologies, but their software, and that programmed perception of shared abstract reality called cyberspace. People are vulnerable to exploitation because with the way the internet has currently been built, computer programmers and software administrators must be trusted not to exploit people through the virtual reality they encode for us. But trusting people is a demonstrably poor security strategy. Section 5.4.7 Software Security Challenge Number 6. Software entrusts people with unprecedented levels of asymmetric abstract power and control authority over our vital digital resources. The author has now identified 5 different ways that software's lack of physical constraints contributes to challenges associated with software security. Because state mechanisms have infinitely expandable state spaces, there is practically no limit to what software engineers can design. Because software represents abstract meaning assigned to state changes as machine-readable language, software designs are abstract and physically unconstrained. Being physically unconstrained means software system designers have nothing physically limiting them from producing unmanageable or outright logically flawed designs with runaway complexity. The combination of infinite state spaces and physically unconstrained complexity means software can have an infinite and unmanageable number of hazardous states. Being physically unconstrained also means it's easy to build invisible, complex, and unmanageable control signal interfaces where engineers don't even know what control signals are being passed to the computer. Moreover, the discrete, non-continuous nature of state mechanisms means software is just one wrong move away from sudden and unpredictable behavior changes. There is another reason why software's lack of physical constraints contributes to systemic security problems, one that surprisingly few scientific papers have mentioned. Software gives administrators highly asymmetric levels of abstract power and control authority over other people's computers, and there's often no way for users to physically constrain software administrators from systemically exploiting or abusing their special permissions or control authority. In other words, software represents a new form of abstract power hierarchy, where someone with extraordinary amounts of abstract power must be trusted not to exploit it. As discussed at length in the previous chapter, abstract power hierarchies are trust-based, permission-based, and inegalitarian systems that are demonstrably insecure against untrustworthy people. Ironically, the asymmetric abstract power and control authority given to software administrators is derived from an attempt to make software more secure. Sometimes it's not difficult to recognize a software system's hazardous states and sensitive control signals. For example, consider a simple piece of software responsible for managing private or sensitive data, or a piece of software which controls the firing of a weapon system. For both systems, there are control signals which would qualify as sensitive or unsafe control signals that should either be eliminated or logically constrained. Because software is abstract and non-physical, software engineers must use logical methods to constrain these control signals. They can't use physical constraints like physical interlock or a safety switch. Without a way to physically constrain sensitive control actions, a common alternative that software engineers like to use to logically constrain sensitive control signals is to codify permission-based or rank-based hierarchies, where special permissions are given to specific users to execute sensitive control signals. By using this technique, software engineers effectively codify abstract power hierarchies for themselves, where some users, in other words, a ruling class, have more rank and control authority over low-ranking users, in other words, a ruled class, and must be entrusted not to abuse or exploit their rank. For example, it is not uncommon for software to give certain users admin rights. Incidentally, these rights are colloquially known as God rights because of the amount of abstract power and control authority they have in comparison to regular users with regular permissions. These systems are systemically insecure by virtue of the fact that users must trust their admins not to abuse their admin or God rights. Because software is an abstraction, all permission-based control structure designs like this qualify as abstract power hierarchies. Software engineers are essentially forced to encode these abstract power hierarchies to logically constrain control authority, because they simply don't have the option of using real-world physical power as the basis for constraining control authority, at least not before the invention of Bitcoin. Here we see the lack of physical constraints in software creating yet another major systemic security vulnerability. Without being able to physically constrain sensitive commands, software must necessarily use centralized, trust-based, permission-based, and inegalitarian systems of control, where users are inherently vulnerable to systemic exploitation and abuse by untrustworthy or unethical computer programmers and software administrators who award themselves asymmetric abstract power and control authority over the system via specially encoded privileges and permissions. The previous chapter provided a lengthy and in-depth discussion about the systemic security flaws of abstract power hierarchies. As it turns out, the systemic security flaws are the same whether abstract power and control authority is codified using rules of law or using software. The fundamental security flaw of these systems is derived from the lack of control over the higher-ranking positions. Users must necessarily trust in the benevolence of their God kings, in other words, software administrators who have God rights over the software, because they otherwise have no ability to physically constrain them for being systemically exploitative, abusive, or incompetent with their asymmetric levels of control authority. Rank-based control structure design approaches only restrict those who have permission to access sensitive control signals. They do nothing to physically constrain the execution of sensitive control signals. Consequently, there is little to nothing stopping a higher-ranking computer programmer from executing unsafe control actions which could cause the system to enter a hazardous state. Recall the lessons of the previous chapter about how logical constraints can't stop the exploitation of logic, They can only change the logic that can be exploited. Therefore, just like all abstract power hierarchies which assign rank and special permissions to specific users, users must trust higher-ranking insiders not to abuse or be incompetent with their ability to send or withhold sensitive control signals. Likewise, users must trust that software developers design the system in such a way that outsiders can't exploit the hierarchical control structure to gain access to the special permissions and control authority given to higher ranks. Regardless of whether a rank-based resource control structure is formally codified using rules of law or software, whenever special permissions are granted to specific ranks within an abstract power hierarchy, the same systemic security problems emerge. Abstract power is inegalitarian, trust-based, permission-based, systemically endogenous, and zero-sum. But perhaps most importantly of all, rank-based control structures create a honeypot security vulnerability. Positions of high rank and control authority have a high benefit to exploit or attack. In other words, a high benefit of attack. It's far easier for untrustworthy or belligerent actors to exploit people or gain disproportional access to resources by taking over high-ranking positions in rank-based control structures. Creating rank-based control structures comprised of high-ranking positions with lots of disproportional control authority over computers is like lighting a flame in a dark room filled with moths. If you build rank-based abstract power hierarchies, systemic predators will be attracted to those positions. To make matters even worse from a systemic security perspective, software alone cannot impose severe physical costs on anyone attempting to exploit or abuse a computer program's control signals. No matter how well software's control structures are designed, software alone has no capacity to physically constrain the execution of unsafe control signals. The only way this can be done is to physically constrain the underlying computer. Not being able to increase the physical costs of executing unsafe control signals, in other words, increasing the cost of attack, means the benefit to cost ratio of attempting to access and exploit the centralized control structure of a computer-instantiated abstract power hierarchy can only increase as more people use and rely on it. In other words, BCRA can only increase. Users are physically powerless and therefore wholly reliant on a specially permissioned group of administrators to keep them secure. Eventually, the BCRA of exploiting a software's control structure can reach a hazardous level that will motivate someone, either inside the system or outside the system, to exploit it. The systemic security of software-instantiated abstract power hierarchies therefore hinges on both the design skill and self-restraint of the software engineers and administrators. Computer programmers must be trusted to design a hierarchical control structure that can logically constrain people from exploiting a computer program's sensitive control signals. Then, the programmers themselves must be trusted not to give into the increasing temptation of taking advantage of the increasing benefit-to-cost ratio of attack of the hierarchical and asymmetrically powerful control structures they have designed. Unfortunately, the history of all abstract power hierarchies created over the last several millennia is filled with examples of breaches of that trust. Just like abstract power hierarchies codified by lawmakers, those codified by computer programmers are apparently just as vulnerable to attack from bad actors, either external or internal to the system. These vulnerabilities have now blossomed into wide-scale systemic exploitation and abuse across cyberspace. Computer engineers and administrators of all kinds wield extraordinary levels of asymmetric, abstract power and control authority over cyberspace, and the evidence of wide-scale systemic exploitation and abuse of people's digital information and computer resources has become commonplace.